As you can imagine, when we look at a function, quite often we're interested in finding its maximum and minimum value. So in this section, we're going to focus on the definition of what we mean by saying a maximum and minimum and how we can go about finding them. We will start by defining what we mean by an absolute extreme value and a local extreme value. So if we have a number c as part of a domain of a function f, then f of z is referred to as an absolute maximum if that value of f of c is bigger than all the other f of x's for any x in our domain. Right? So when I evaluate f at c, then f of c is bigger than any other value. That would make my function, my value, an absolute max, and it would be an absolute minimum if f of c is smaller than f of x for every other x in our domain. And f of c is referred to as a local max if f of c is bigger than f of x for all x's that are near c. So maybe not for every value in our domain, but for all the values to the left and right of c. And it would be a local minimum if it is smaller than all of those values. So if I'm looking at this graph, I will have an absolute maximum at f of d. So notice f of d is higher than all the other values on my graph, and I will have an absolute minimum at f of g. So f of g is the lowest value in my graph. I have local maxes at 3 different places. At b, that point is higher than all the other points near it. At d, that point is higher than all the points near it. And at f, that point is higher than all the values near it. And we have local minimums at c and at e. Those 2 points are lower than all the points that are near them. Notice that at f of d I have both an absolute max because that point is higher than every other point, and also a local max because it's higher than all the points near it. While at g I have an absolute min. It is lower than all the other points in the graph, but it's not a local min because it's not lower than the other points to the right of it. Those points are not part of my domain. The next question is, when do functions have these extreme values? So the extreme value theorem tells us that if f is continuous on a closed interval a to b, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d inside of that interval. Now notice this theorem only guarantees an absolute max and min, and only if the conditions of continuity on a closed interval are met. Right, so my interval needs to be closed and my function is to be continuous. So here are a couple examples where we may not have absolute maxes or mins. So in this function, our domain is on an open interval. At one end I have an asymptote, and at the other end the value of the function is not included, and my function does not have an absolute max or min. Where I would have had an absolute max to the left here, the graph is not defined, and where I may have had an absolute min, I have an asymptote and I do not include the endpoint. here is a graph where I have a closed interval. It's both endpoints of that interval are included in my function, but my function is undefined. No, I'm sorry, is a discontinuous right here in the middle. It's undefined over here. The function's defined a little higher. And if I was trying to find an absolute minimum, it would have been down here, but my function is not defined at that point. There is a jump discontinuity. It does have an absolute max at one end. So notice this doesn't mean that discontinuous functions cannot have an absolute max or a min. Only that we don't have a guarantee that the function does have a max or a min. If I switch the open and the closed points here in our graph, we still have a discontinuous function, but it would have an absolute min down here and an absolute max. So the extreme value theorem told us when a function would have an absolute max or min, but not how to find them. Our next theorem tells us where to look for a local max or a local min. Fermat's theorem says if f has a local max or min at C, and if f prime of C does exist, then f prime of C must be 0. Right? So again, let's make sure we understand what it does not tell us. Got to be careful. It does not say that if the derivative is 0, we necessarily have a local max or min. The derivative of a function can be 0 at a point, and that point may not be a max or min. This says if I have a max or min, then the derivative would be 0 if it exists. So it gives us possible places where I may have a max or min, or where I should be potentially looking for a max or min. Right? So if we go back and look at our function where I had local maxes and mins, at some of them at least, the derivative was 0. So the derivative being 0 means if I drew a tangent line, I would end up with a horizontal tangent. And that should make sense. If I have a peak or a valley, all the way at the top, I should have a horizontal tangent. So at the 4 of the possible places where I had local maxes or mins, the derivative was 0. Notice that at D, we still had a local max, but at that point, the derivative is undefined. So as the theorem suggests, the derivative will be 0 if it does exist. So at that point, f of D, the derivative did not exist, and therefore it does not follow this theorem, even though I did have a local max or min. Next, we will introduce some new terminology so we can refer to these points of interest as critical numbers. So a critical number of a function f is a number c in the domain of the function, such that either the derivative is 0 at that point, or the derivative does not exist. So as we find the derivative, the locations where the derivative is 0 or the derivative does not exist are what we refer to as critical numbers. That allows us to reward Fermat's theorem in the following manner. If f has a local maximum or minimum at C, then C is a critical number of f. So either the derivative doesn't exist or the derivative is 0. So combining the extreme value theorem and Fermat's theorem gives us a method of trying to find the absolute maximum and minimum for a function on a closed interval. So in this method, first thing we are going to do is find the derivative of our function and the critical numbers, and then evaluate our function at those critical numbers. So we find the critical numbers, plug them into our function, find the value at those points. Do the same thing for the endpoints of our interval. So find f of a and f of b. And then look at all the values we have found. So the function evaluate at our critical numbers and the function evaluate at the endpoints, and find the largest value and the smallest value. Those would be our absolute maximum and minimum. So here's an example. So what we have here is something we call the Allais effect, that tells us that certain populations decline to extinction once they fall below a critical population size. And here is a simple model that follows that. F of n is equal to n times n minus 3 times 8 minus n, where n is the population size in hundreds at time t. And we want to know what's the absolute maximum and minimum growth rate when n is between 0 and 10. So first thing we're going to do is simplify the function we had by distributing the two parentheses and n together. We get a polynomial which is easier to take the derivative of. Those parentheses distributed together gives me negative n cubed plus 11n squared minus 24n. Take the derivative of that function. I'll end up at negative 3n squared plus 22n minus 24. And that can be factored. We can take out a negative out, and the remaining trinomial factors into 3n minus 4, n minus 6. Now, to find our critical numbers, we need to know when this is undefined and when it is 0. It's a polynomial, so it's always defined. I don't have any places where my derivative is undefined, but I have a couple places where it is 0. If I set each parenthesis equal to 0, I get n equals 4/3 and n equals 6. So I have two critical numbers, 4/3 and 6. Now, if you recall, the next thing we need to do is evaluate our function at 4/3, 6, and at the endpoints, 0 and 10. So there are 4 potential places where I could have an absolute max or min. If I evaluate my function at 0, I get 0 times 0 minus 3 times 8 minus 0, and 0 times anything is 0, so that value gives me 0. Plugging in 10 into our function, we have 10 times 10 minus 3 times 8 minus 10. That gives me negative 140. When I plug in 4/3 in, I get negative 400 over 27, which is a little more than negative 14. Or, I'm sorry, a little smaller than negative 14. And finally, when I evaluate my function at 6, I end up with 36. So looking at the values we had, 0, negative 140, negative 400 over 27, and 36, the largest value we have is 36, which would be our absolute max, and the smallest value we have is negative 140, and that is our absolute min. So the population grows fastest when it reaches n equals 6 or 600, and the maximum rate of increase is 3,600 individuals per year, and it decreases most rapidly when the population reaches n equals 10 or 1,000. So the absolute minimum rate at which the population is decreasing is 14,000 individuals per year.